So let's start with section 2.8, implicit differentiation. So far we have seen examples where we can express y in explicit form. That means that there is some equation, y equals some function of x. And this is called explicit form. But sometimes relations between y and x are complicated, and sometimes you cannot express y in terms of x. Instead of that, there is what is called implicit form, and that means that there exists some function capital F, say, that depends on two variables x and y, and the relations between x and y are expressed in the following form, that this function is equal to 0. The point is that we know how to find the derivative in the first case when we have explicit form, but also in fact we can find the derivative if we have implicit form as well. So what are the examples? So examples of explicit that we know, say y equals 3x squared minus 2. And now let's consider an implicit example. And this is an example from the textbook where we have an equation of the circle x squared plus y squared is equal to 25. So, or we can write down it's in the following way: x squared plus y squared minus 25 is equal to 0. So my capital F of x and y from the definition will be thus x squared plus y squared minus 25. And then the relations can be expressed in form that capital F is equal to 0. Of course, in this particular case, you can solve this equation in terms and express y in terms of x, and it's not difficult to do. So it's just square root of 25 minus x squared plus minus, right? And this is now it becomes explicit form. But the point is that sometimes you cannot do that, and we will see such examples. But in this example, we can compare two techniques. We will find the derivatives in two ways. So let's focus on the upper half of the circle. So let's consider y equals square root of 25 minus x squared. So let's consider upper half. So we have this unit circle. Oh, not units, it's with a radius 5, because 25 is 5 squared. 5 squared. So let's focus on the upper half. And let's calculate the derivative. We know how to do that now. And one of the way is, for example, the chain rule. So I have what? Oh, maybe generalized power rule. Say generalized power rule. Y prime. So it's 25 minus x squared to the power 1/2, and derivative of this stuff. And by the generalized power rule, maybe it's better to put here. Power rule. It is derivative of the power function, so it's 1/2, 25 minus x squared to the power 1/2 minus 1, times the derivative of the function inside, so it's 25 minus x squared derivative. And so that gives me 1/2, 25 minus x squared to the power minus 1/2, times derivative of the difference is difference of the derivatives, and derivatives derivative of 25. So this is the same as 25 derivative minus x squared derivative. Derivative of the constant is 0, while derivative of x squared gives me minus 2x. So finally, that gives me minus 2x on the top, 25 minus x squared, square root of that, and 1/2 in front, so I still have some cancellations of 2, and the very final answer is minus x divided by 25 minus x squared. In the textbook, they focused on the lower part of the circle, but it doesn't really matter. And suppose we want to calculate our derivative at 0.4. So we just substitute and get that it's minus 4 divided by square root of 25 minus 4 squared, which is 16. 25 minus 16 is 9. So it's minus 4 divided by square root of 9, which is minus 4 over 3. And this is the final answer. This is the way how you can calculate the tangent line of the circle at 0.4. So that will give you, so somewhere here is 0.4, and this is the slope of this tangent line. It's negative, that's why it's going from upper left to the lower right. Minus 1/3. And of course, if you repeat the same story with the lower part of circle, then you'll get this, this tangent line. And this corresponds to the choice minus here. But that's what I don't want to do. Instead of that, we will implicit differentiate our equation of the circle. So what does it mean? It means that the second way, implicit. So let's start again with our equation. X squared plus y squared is equal to 25. And the point is that we can differentiate equations. So let's consider derivative of the both sides. So d over dx of this should be equal to d over dx of 25. And so, again, derivative of the constant is 0. Then we have d over dx of x squared plus d over dx of y squared. And with the first term, it's simple part, because this is just derivative of the x squared, so that gives me 2x. While here, for the second term, I have that a function of x, which is y squared. And again, I can use generalized power rule, right? So I have y squared of x derivative. All right, and let's recall that dy over dx to the power n is equal to, where y is function of x, and y to the power n minus 1 times dy over dx, right? This is our generalized power rule. So it's almost like a power rule, except that you need to add extra derivative of the function itself. And so the second term, so the first term gives me 2x, while the second term, by this rule, gives me 2y times dy over dx is equal to 0. And so what I got? I got some equation where what I need to find is my derivative. And so I can express it. So dy over dx will be, I can put 2x on the right hand side and get minus 2x And then dy over dx thus will be minus 2x over 2y, or just minus x over y. So what we got, the derivative of our circle, equation of the circle, is equal to minus x over y. And we already can see the difference, because before we got that our derivative here, okay, let me maybe write it like that, dy over dx is equal to minus x over square root of 25 minus x squared. That our derivative was expressed in terms of x. There is no y here, right? While here we get that it's sum. In the numerator we have x, while in the denominator we have y. And this is the usual price that you need to pay for the implicit differentiation, that you can find the derivative in that case, but usually the derivative will be expressed not only in terms of x, but also will involve y. Of course, I can use the equation that y squared plus x squared is equal to 25 and get that y is equal to square root of plus minus square root of 25 25 minus x squared, and plug it here and get that it is the same minus x over square root of 25 minus x squared. That's what we got before. But again, this is kind of baby example where you can do both cases. And in the next case, not next, but maybe after a few examples, we'll see complicated equation where it's impossible to express y in terms of x. And in that case, you do not have first way, because there is no way to write y as a function of x, but there is still a way to calculate the derivative. And that's it. Okay, question so far with this first example. So what is the main point? Again, the main point is that you can differentiate an equation. That's what's the crucial step here. And when you differentiate, you should remember that y is a function of x. So you cannot write that derivative of y squared is just 2y. No, because you differentiate with respect to x. What you should add y prime here, and then it becomes correct equality. Okay, more examples. Example number 1 from the textbook. A, which is 3y cubed, is equal to x, and we want to find the derivative of y. Again, you can express y in terms of x in this case, but let's practice with the implicit differentiation. So again, first step is to consider the derivative of the both sides. So we got 3y. Derivative of this should be equal to derivative of x. Derivative of this, again, by the generalized power rule, is 3 times 3y to the power y squared times derivative of y. And on the right hand side, I have 1. And so I get 9y squared times 9 prime, or y prime, is equal to 1. And so y squared thus will be, oh, sorry, not y squared, because I want to express derivative. So y prime will be thus 1 over 9y squared. Okay. And that's it. And I want to say, if I want to calculate, for example, at point y, suppose you know the y coordinate where you want to calculate your derivative, say y equals 1, for example, then and some x that corresponds to this y, then the derivative at that point, okay, let's say that have some point p with coordinates x0 and say 1, then y prime will be 1 over 9 times 1, of course, but this is 1 over 9. Okay. This was A, part A. Part B is the following example: x squared y squared is equal to 1. And again, let's calculate the derivative of both sides. Y squared, which is again derivative of 1 on the right hand side. And here I have a product, right? I have two functions and the product of them. So I should use first, I should use the product rule, right? So that will give me derivative of the first times second plus first times derivative of the second one. And on the right hand side, I have 0. Okay. And this is again easy part. It's just 2x. This is again by the generalized power rule, gives me 2y times y prime. And so I get that it is 2xy plus 2y x squared y prime, and it is equal to 0. And again, I get an equation that involves my y prime. That's what I'm looking for. So y, okay, let me write it slightly more accurately, is equal to minus 2xy, put it on the right, and then y prime thus will be minus 2x y divided by 2y x squared. And so I have some cancellations. Y prime is equal to 2x and 1 power of x. Oh, am I correct? Ah, yeah, y squared. That's what I missed. Y squared, 2x, y squared. Otherwise, I have too much cancellations. And 1 power of y. So I get that it's equal to minus y over x. And part C, it's quite similar. X squared y is equal to 4. The algorithm is the same. So differentiate. Now let me write instead of d of dx, write me in this notation. Y prime is equal to 4 prime. And again, I have a product of two functions, x squared and y. And by the product rule, it is derivative of the first times second plus first times derivative of the second. And on the right hand side, I have 0. Let's slightly modify it, so I get, say, 4x on the right side. And then I will get 4. So in general, you don't have to have constant on the right hand side. It can be another function. And so you'll get just 4. And then what you'll get? You'll get 2x times y plus x squared times y prime is equal to 4. So y prime thus will be x squared y prime will be 4 minus 2xy, and y prime thus will be 4 minus 2xy divided by x squared. Okay, this is the final answer. This is the final answer, and this is the final answer for 3 cases. Okay, it is modified, say, C tilde. Okay, let's go further and discuss example 2. And this is, so before it was like a practice, and exercise example 2 is the usual problem where you need to differentiate the function implicit. Plus 4x cubed y to the power 4 plus 2y is equal to 4. And again, now we have some summons, but the algorithm is still the same. You just need to differentiate both sides. And so again, for short notation, I will use primes instead of d over dx. So again, the derivative of the sum is sum of the derivatives. So it's 3x squared prime plus 4x cubed y to the power 4 prime plus 2y prime is equal to 0. With the first one, again, just the polynomial, so it gives me 6x. Second one is the most complicated one, so I can put 4 in front of that. And let's do it in a few steps. X cubed y to the power 4 prime plus 2y prime. So I can put constant 2 in front of the derivative, and then I'll get just y prime. And what is about this term, x cubed y to the power 4 prime? First, I need to use the product rule. Because it's a product of 2 functions, and that gives me x cubed derivative y to the power 4 plus x cubed times derivative of y to the power 4. And that gives me 3x squared y to the power 4 plus x to the power 3. And here I'm using again generalized power rule. So it is 4y cubed. So it's part of the just power rule, but I need to multiply by the derivative because y is a function of x. And this is my second term. So combining all terms, I get 6x plus 3x squared y to the power 4 plus 4x cubed y cubed y prime. This is my second term. And plus 2y prime should be equal to 0. Okay. And there is something new, because before we had only one term that contained derivative of y, while here we have y prime here and here. But again, you should think about that as ordinary linear equation where the unknown is y prime. And to do the usual steps to solve. So what are the usual steps? Put everything that doesn't contain y prime to the, say, right-hand side, and keep all the terms that contain y prime on the left-hand side. So let's do that. So I get 4x cubed y cubed times y prime plus 2y prime is equal to minus 6x, because I put it on the right, and minus 3x squared y to the power 4. Okay, then y prime is a common factor, common multiplier, so I have that y prime times 4x cube y cube plus 2 is equal to, let's say, minus 6x plus 3x squared y to the power 4. And the last step, so this is kind of coefficient in front of my unknown, and I need to divide by that coefficient. Y prime is equal to minus 6x plus 3x squared y to the power 4 divided by 4x cube y cube plus 2. Oh, okay, I made a mistake because I forgot this coefficient. So here should be 4 times that. Sorry for that. Okay, so what will be changed? So I get, sorry. Y to the power 4. Yes, so it is. Okay, so it will be 16 here. And it will be 12 here. So it will be 12 here. Sorry for that. 12 here and 16 here. And so it is 12 here and 16 here. And I can divide numerators and denominators by 2 and get that it is that y prime thus will be minus 3x plus 6x squared y to the power 4 divided by 8 x cube y cube plus 1. Okay, now it's the correct answer. In this example, we cannot express y in terms of x, right? Because we have y to the power 4 times some coefficient that involves x, and also you have y here. And so you get non-linear equation of the 4th order. And even the linear equation of the 4th order doesn't have a solution in general using the radicals. So there is no way that you can express y in terms of x. And you cannot find the derivative explicitly. But the good point that you can still find the derivative using the implicit technique. Let's do one more. So now you can use this technique to solve the problems that contains slope of the tangent line. So what is the tangent line to the curve y x squared minus 3xy plus y squared plus 4x minus 2y is equal to 1 at point 1, 4. Okay, so again, we remember that to find the slope of the tangent line, we need to calculate the derivative to the curve at this point. And so we need to find y prime 0.1. And again, we have kind of quadratic equation for y, and it's not linear because we have 3x times y, and that means that it is, again, impossible to express y in terms of x, so we have only one way, implicit differentiation. And what I want to say, yes, so let's follow the algorithm, consider the derivative of the both sides, plus 4x minus 2y is equal to derivative of 1. And derivative of this will be 2x minus the derivative of the product. All right, so we have, okay, let me write it like that, plus derivative of y square I can write and right now because we discussed it several times. It's generalized power rule, 2y times y prime plus 4 and minus 2y prime, and everything is equal to 0. And here I will use product rule that gives me x prime y plus plus x times y prime, and this is y plus xy prime. And so I get 2x minus 3 times y plus xy prime plus 2y y prime plus 4 minus 2y prime is equal to 0. Again, long expression, but what I'm looking for is just y prime. So I again collect all the terms that contains y prime, and I get minus 3xy prime plus 2y y prime minus 2y prime, and put everything on the other side. So that is 3y minus 2x and minus 4. And again, y prime is a common, and I get minus 3x plus 2y minus 2. Y prime is equal to 3y minus 2x minus 4. And the last step is to divide by that coefficient and get that y prime is 3y minus 2x minus 4 divided by 3x plus 2y minus 2. Okay. And this is the final answer, or not the final answer, because now I want to find y prime at y prime point P that has coordinates 1, 4. So y prime thus will be 3 times 4 minus 2 times 1 minus 4 divided by y prime evaluated at point P. And minus 3 plus 2 times 4 minus 2. So it's 12 minus 2, 10, 10 minus 4 is 6, over minus 3 plus 8, which is 5, 5 minus 2 is 3. So the final answer is 2. So that means that the slope of tangent line M is equal to 2. And again, recall the equation for the straight line. Y minus y naught is equal to M times x minus x naught. And our P has coordinates 1, 2. And again, the tangent line should go through that point. That means that y minus 2 is equal to 2 times x minus 1. And I can simplify it and get that it is 2x minus 2 plus 2. And finally, y equals to 2x. I found not even the slope, I found the whole tangent line. In the textbook, it was just the slope. But it's good to recall how to find the whole tangent line. And the last example in this section is this one. Now it's find the equation of the tangent line, so I will find just the slope. 3x slope of the tangent line at point 3 minus 3. Again, what we can do, we can use our strategy. So 2y y prime is equal to derivative of the right hand side, which is just 3. I will do it slightly fast, but I think you understand what I'm doing using the, again, implicit differentiation. So y prime will be 3 over 2y. And y prime at point P will be thus 3 over 2 times minus 3, so it's minus 1/2. This is slope M. Okay, and what I wanted to say before the remark, that sometimes, as before, we have seen that usually in such problems you have two coordinates. So as in this case, you have point is coordinates 3 and minus 3. So you know both coordinates, x and y, and then you plug to the your formula for the derivative and find the derivative. But sometimes you can have only x coordinates. So suppose you want to find the derivative of the following function. I mean, even of this function, but at point, and you know that just x is equal to just 3, no y. So suppose you have y squared is equal to 3x, and what is the y prime at point 18, for example. So what is the difference? Difference is that you know only the x coordinates of P. So P has coordinates 18 and something that you don't know from the beginning. So if you repeat the steps, you will get again that y prime is equal to 3 over 2y, but now you have a problem because you don't know the y coordinates, right? You don't know what to substitute here, right? And the way to solve such problem is to come back to the original equation. So we have y squared is equal to 3x, and how to find the y coordinates if x equals 18. So we get that y squared is equal to 3 times 18, which is 30, what I'm saying, 54. What's wrong? Just a moment. Not 18, what I wanted. 27. Sorry. Let's for the nice answer. Let's do 27. 27. So you get 3 times 27, which is 81. So that means that y is equal to plus minus square root of 81, which is plus minus 9. And this is your y coordinates. Now you can calculate your slope. So your slope will be 3 over 2 times 9 plus minus, which is plus minus 1 over 6. So again, what is the point of this remark? That sometimes it's not common, but you can see such problem where you don't know the both coordinates, but only one, say x. And to find the another one, the second one, you have to solve, you have to plug your known coordinates to the initial equation and find the second one. Of course, usually both coordinates are given, because even if you, for example, even if you plug, say, x equals 1 in this example, you'll get quadratic equation for y that you need to solve, and it's a lot of work, right? So if you just know that you are looking for tangent line at point x equals 1, then what you'll get 1 minus 3y plus y squared plus 4 minus 2y is equal to 1. And that will give you y squared minus 5y plus 4 is equal to 0. And you need to solve this quadratic equation and get that y. One solution is that y is equal to something wrong, to 4, and another is 1 minus 5, yes. And so it's extra work, and again, sometimes if you get cubic equation for y, it's sometimes even impossible to do. But I just wanted to make that remark, how you can do that if you know only one coordinate. What I want you to do is the following part of the homework. It is exercise 34. I think I have included it in the homework list, but let me emphasize that there is derivative of this function p over q. So remember, we discussed that it's easy to obtain the power rule when n is integer, but it turns out that it's true for all rational numbers. That means that n is equal to some ratio of p and q, where p and q are integers. And the point is that if you have such equation, you probably know what is the next step. You can reduce it to our case, to our kind of usual case with integer power by considering q's power. So what I'm saying, y to the power q will be u to the power p. I don't know why they used u, but we can use x. Maybe it's x to the power of p. And then you need to differentiate this implicitly and express y prime. And so the strategy is this implicit differentiation. And from that, you will get that y prime will be p over q, x to the power p over q minus 1. And that will prove our power rule in case when the power is rational. Section 2.9, which is called higher derivatives. If you have displacement s that is function of time, then we remember that we can find the velocity will be time t will be derivative of our function ds over dt, and we defined the acceleration by the derivative of the velocity, right? But we can continue that, and that's what we did that time, because velocity is itself a derivative of x, so ds over dt. And we also gave the notation for that. We wrote that it is d squared of s over dt squared. Okay. Dt squared. And this is example of the second derivative. But also you can consider, say, third derivative. That is denoted by d to the power 3 over dx cube of, say, some function of x, which is just the derivative of the second derivative of my function. And we can define any higher derivative by the induction formula. So what I'm saying that nth derivative is defined by this d to the power n over dxn of some function f of x is derivative of the previous higher derivative. So that means that if you want to calculate, say, fifth, you need to find the fourth derivative, and if you want to find the fourth derivative, you need to calculate third one. If you need third one, you need to second one. If you need second one, you need to find first one, and so on. So you start with first, then differentiate, get second, differentiate, get third, and so on. And other notation is like that, with f prime, f double prime, f. So this is the third derivative. Usually you don't put 4 primes. Instead of that, you write 4 f to the power 4, but with parentheses like that, f to the power f to the power 5, and so on. So again, f to the power 4 with parentheses is not, it's not f to the power 4, but it is fourth derivative of my function. Okay, so don't forget to write parentheses. That's a big difference. Okay, let's see some examples. So suppose you have the function which is 3x cubed minus 2x plus 5. Then y prime, first derivative, will be what? It will be 3 times 3x to the power 2 minus 2 plus 0. So it's 9x squared minus 2. Then second derivative will be the derivative of the first derivative. So it is the derivative of the expression that we just found. And it will be 18x minus 0. And third derivative will be derivative of the second one. And it will be derivative of this, just 18x. And that will be 18. Fourth derivative, I can derivative of the third one. So it's derivative of the 18, which is 0. And then if you continue differentiate, of course, you differentiate 0 and get 0. So all other, so y5 will be the same as y6 derivative, 7th derivative, and so on. All of them will be 0. Okay, so again, this is nothing else but the definition. So you just continue differentiating until you get the desired higher derivative.